Welcome back to section 3 of chapter 8. In this section, we are going to be looking at relative rates of change. This is going to involve finding limits as x goes to infinity and also using L'Hopital's rule, which we just saw. So, our learning targets today, compare the growth rate of functions using limits, compare the growth rate of functions using graphs, and answer conceptual questions involving relative rates of growth. So, first of all, comparing rates of growth. What do we do to compare rates of growth? Well, we're going to divide the two functions. And then we're going to take the limit as x goes to infinity and see what we get. If f of x grows faster than g of x, then when we take the limit as x goes to infinity of f of x over g of x, we will get infinity because the top one is growing faster, right? So it's going to just keep getting bigger and bigger and bigger. Or if we had that flipped upside down, if the faster growing function's in the denominator, it's going to equal 0. So when we take the limit as x goes to infinity and we get infinity or 0, then one of the two functions is growing faster than the other. They grow at the same rate if you get some number that's not 0. So it could be 2, it could be 1/4, it could be 17, it could be pi. Just something that's not 0 and not infinity. And that tells us that they grow at the same rate, which is a little bit confusing. We'll see that in a second. So how can we do that? Show that the function e of x grows faster than x squared as x goes to infinity. So what we're going to do here is we're going to take the limit as x goes to infinity of e to the x over x squared. Now when we plug in infinity, we're going to get infinity over infinity, which we can't really do anything of, and so we have to do something else, which, oh, we're not going to factor this and cancel, so we're going to go to L'Hopital's rule. So we're going to take the derivative of the top and the bottom separately and find the limit as x goes to infinity of that. The derivative of e to the x is still e to the x. The derivative of x squared is 2x. Plug in infinity, we still get infinity over infinity, so we have to do something else. We'll use the L'Hopital's rule again. Limit as x goes to infinity, derivative of e to the x is still e to the x, and the derivative of 2x is 2, which we get infinity over 2, which is infinite. So e to the x grows faster. So that's the basic idea here. Let's look at another one. Let's show that the function natural log x grows slower than x as x goes to infinity. So we're going to do the same thing. We're going to go natural log or limit as x goes to infinity of natural log x over x. Yes, we have both limits and natural logs. You can tell the difference. These are the only two things I ever write in cursive. The difference is that the limit, I do dot my I on the I there. So that's what it is. But you wouldn't have the limit of x over x. That just seems weird. So we have natural log x over x. If we plug in infinity, we get infinity over infinity because the natural log of x is a constantly increasing function. It will go to infinity eventually. But we have to do something else. So let's L'Hopital rule it again. So we get the limit as x goes to infinity of the derivative of natural log x is 1 over x over 1, which is just 1 over x. When we plug in infinity, we get 1 over infinity, which is 0, because as we're dividing by bigger and bigger things, we get 0, which means the denominator grows faster, which means the numerator, natural log x, does grow slower than x as x goes to infinity. So these are the two ways that could look. Fun story. compare the growth rate of the functions 2x and x as x goes to infinity. So we have 2x and x. So obviously 2x is growing faster, right? Limit as x goes to infinity of 2x over x, we can cancel out an x, and we get this equals 2, which is a number that's not 0. So these actually have the same growth rate. And you might be thinking that, wait, that does not make sense because 2x, I mean, that has a slope of 2, x has a slope of 1. By our definition here, they're the same. So how do we make sense of that? They're both growing linearly. Their rate of growth, like the rate of change of their growth, is not actually changing. It's a constant growth for both of them. And so they're both growing at the same rate. Whereas, say, the e to the x, I mean, that graph is curving, right? And it's getting steeper and steeper and steeper faster than x squared is getting steeper. So the rate of change of the rate of change is increasing a lot faster. In this case, the rate of change of the rate of change is 0. So it's a way to help make that make sense a little bit. So let's do a couple more examples here. Show the function x grows at the same rate as x plus sine x as x goes to infinity. So we're going to take the limit as x goes to infinity. Again, this is what we're doing. There's not a lot of variation here in what we're doing, but how we find the limits can change. Because we're going to have x plus sine x over x. If we so first of all, let's make conceptual sense of this. So show that the function is growing at the same rate. So x and x plus sine x are growing at the same rate. So if we think about x and x plus sine x is just going in between -1 and 1, which when we're at really small values of x, 2, 3, 4, that makes a bit of a difference. But when x is 1,000, does it matter? Like, does that plus or minus 1 really make a difference when we divide by 1,000? I mean, 999 divided by 1,000 and 1,001 divided by 1,000 are basically the same, and 1,000 is still a relatively small value of x. So it should make sense that these guys are growing at about the same rate. So how do we find the limit here? We're not going to factor stuff out. If we use L'Hopital's rule and we find the derivative, we'll have 1 plus cosine x over 1 as x goes to infinity. That doesn't have a limit. So what can we do? We can split this up. So we can make this the limit as x goes to infinity of x over x plus sine x over x, which is 1 plus sine x over x. So now when we plug in infinity, the sine x is going from -1 to +1. It's not changing that much. It's a small value, and x becomes infinite. So we have that whole piece becomes 0. So this is going to be 1 plus 0, which is just 1. So our rate of growth we take the limit of the ratio there, we get 1, which means that they have the same rate of growth. If we wanted to graph this to see, this is the graph of x plus sine x over x. Notice very, very quickly, it stops going up and down a bit, and it is just sitting right at 1. I mean, it's still oscillating either side, but it's by smaller and smaller values. So we can see that this limit is going to 1 as x goes to infinity. That, looking at a graph like this, is another way of seeing it. Now the trick is, if I was using the normal viewing window, which would stop right about here, we would not be able to see that. You have to zoom out specifically in the x values. Notice my x values here are going out to 500. That was enough to give me a pretty decent idea that this is where it's going. It's not going to start doing something crazy after that. So we can always look at the graphs as well. And that can help. How about some logs? So here, let a and b be numbers greater than 1. Show that log base a of x and log base b of x grow at the same rate as x goes to infinity. It's kind of an interesting one. We can go the limit as x goes to infinity. Let's go log ax over log bx. And now if we plugged in infinity, like the bases, it's still going to go to infinity. It's just we don't know exactly how. What's showing that it's growing at the same rate, it should be going at about the same. What can we do here? Log properties, specifically change of base. If we use the change of base property here, we get natural log x over natural log a over natural log x over natural log b. We can change them to the same base, specifically natural log, because if we're going to have to take the derivative, the natural log is way easier. We can simplify this a little bit. We could flip and multiply the denominator. Natural log x's cancel, and so we get x is going to infinity of natural log b over natural log a. Well, a and b are just numbers greater than 1. Natural log of a number is just a number. Here we have a number divided by a number, which is some value of L, where L is not equal to 0, and L is not infinite. And so even though we don't know what that number is, because it doesn't matter what these two bases are, it will be growing at the same rate. Remember, a change of base is a vertical stretch or compression, kind of like x and 2x. It's just changing the slope, but it's still that constant value. So using our log properties is another thing we can do to help us find these limits, because L'Hopital's rule is not always going to work. Although in this case, it would have worked okay, because you take the log of or the derivative of a log, and you get, it splits it out for you. So next one, sometimes we can't necessarily compare two things directly, but if I know that they're both equal to another thing, then they should be equal to each other. That's the whole transitive property thing. And the growing rates also are transitive. So if f grows at the same rate as g, and g grows at the same rate as h, then f grows at the same rate as h, as x goes to infinity for all of these. Again, x has to be big enough. So if we have two things that are the same, and then something else is the same as one of them, that means that third piece works too. This is also true with things that are growing faster than other things. It's like if x is growing faster than g, and g is growing faster than h, then f is growing faster than h. You do need to make sure that the signs are facing the same direction on that for that to work, but it does work. So anyway, I said there are things that we wouldn't necessarily want to compare directly to each other. something like f of x is x, the square root of x squared plus 5, and g of x is 2 root x minus 1 squared. Those two things, that would be ugly to try to compare those. So let's compare them to something else. Let's use h of x equals, and then let's see what this might look like. We have x squared plus 5. Well, the plus 5 is not really going to do much, but the square root. So as x gets really, really big, this is basically the square root of x squared, which is x. The other one, as x gets really, really big, we have 2 times the square root of x squared. So that'd be 4x. So it looks like x might be a decent thing to compare them to. So let's start out with the limit as x goes to infinity of f of x over x. Let's go square root of x squared plus 5 over x. So we can work with these. First thing I would do is let's get the x inside the square root. And so if we want to bring it inside the square root, it has to be squared. That way, when it comes out of the square root, it's just back to x. Then from here, we can separate the fraction. So we have x squared over x squared, which is 1, plus 5 over x squared. So now as x goes to infinity, the 5 over infinity is 0, so it's just the square root of 1, which is 1. So f of x is growing at the same rate as x. Let's try the other one. Limit as x goes to infinity of 2 root x minus 1 squared over x. Same thing, we're going to want to bring it into that squared. This is going backwards from the square root, so to bring it into the squared, we would need it to be a root x, because now root x squared would give us the x that we needed. We can split this up again. So we'd have 2 over root x, which is just going to be, or 2 root x over root x is 2, minus 1 over root x. When we plug in infinity, the 1 over root x, that's 1 over infinity, that's 0. So 2 minus 0 is 2. Squared, we still have that squared. So this ends up equaling 4. So these both come out to be the same. Now, what if we wanted to figure out what it would come out to be by finding the ratio of the two? Well, if we wanted the limit as x goes to infinity of f of x over g of x, we're not doing that separately, but we can split that up. And this is kind of where the proof of the transitivity deal comes from. We could go f of x over x times x over g of x, right? Because the x is canceled and we have f of x over g of x. But we know that the limit of f of x over g of x was 1 times, now the limit of g of x over x was 4. So that means the limit of x over g of x, if we find the reciprocal, that would be 1/4. And so if we did do these directly, we would end up with 1/4. And so we can compare our rates of growth, make a ratio, find the limit as x goes to infinity. If it's infinite, it means the top one's growing faster. If it's 0, it means the bottom one's growing faster. And if it's any other number, it means that they're growing at the same rate. That's the idea for this topic. I'll see you in class, but until then, keep working problems, keep asking questions, and as always, happy mathing.